from process, which has a molar mass of about 9,000, which is not so bad, and the consequence will be very important for the morphologies, because if you look now to the morphologies, here you have the I did something wrong. So if you look to the silicon modified, you have large particle, large agglomerate. If you half modified, so you manage the different interaction with the medium, you have still some large aggregate and small or well dispersed silica. And if you use silica modified with hydroxyl terminated silane, and the chain which are grafted from the surface, now you have a quite nice dispersion of the silica into the system. So the lesson of this part of the work is that by managing the surface chemistry of the silane, the silica from organosilane, you can have a good dispersion of the nanoparticles within the PLA matrix. And the nanocomposite, in that case, morphology is rich. The second route is to have in situ generation of the inorganic phase within the PLA. So the already prepared polymer. Things are done into a micro extruder in which you can have what we call a recirculation of the matter. So you can have a strong effective mixture plus a long time of residence, and we use not directly the precursors. So I mean the silanes, the alkoxysilane, but the precursor, which means high molar mass in order to avoid the removal as you put into the system due to the boiling point. So and the reaction is performed at 180 degrees Celsius. So again, above the crystallization of PLA. We put some water in. We don't need, because we have already some water into the polyester. And the ratio was controlled to be 0.17 in between. We do that and perform the reaction in situ, and we can see that we have, from the beginning, we have Q2 species here, and by NML we see that now we have Q3, which means that we have condensation reaction occurring in between. So we have really soldier process performing in situ, but we have also Q2, still Q2 signal, which means that the condensation is not complete. So what's happening in such a system? How the soldier chemistry works? That works very simply, because at the beginning, from the solubility parameters of the precursors and of the polymer are very similar. So we have a miscible system at the beginning. And as the system condenses to get the final silica type, we can see that the solubility parameters change a lot, which means that as the system hydrolyze and condense, and especially condense, you change the solubility parameters of the inorganic of the organic species, which precipitate during the condensation reaction within the PLA, leading to that kind of morphologies in which we can see here the silicon-rich nanoparticles well dispersed into the system. I will skip this. If we now use the same precursors and add some interfacial agent as methacrylate or amine system, we can get interesting feature in terms of reaction. The idea is to change some thing in the ring opening polymerization, having this amine group, and also to change again the interaction in between and to change the solubility parameters with this methacrylate group. So, but it works, and those systems, and especially the methacrylate, which has a double bond, of course, is located at the interface, and we can see as we stain with ruthenium oxide that the double bonds are located close to the interface, which means that they play the real interfacial agent effect. I was skip those two, because I spent too much time. And third, so again, that's possible using that technique to generate in situ nanofillers, silicon-rich nanofillers, with avoiding the problem of the processing, the initial processing. And that's possible to polymerize the lactide in the presence at the two, to have no change of the PLA matrix as we perform in situ the PLA, some organic-inorganic chemistry. So last example is only the in situ generation of inorganic rich phase, but also combined with the ring opening polymerization. So we come really from the beginning, so the lactide monomer for the organic side, and the precursors from the inorganic side. But we cannot do exactly at the same time, although we already, due to the fact that the polymerization of L-lactide occur at high temperature, so we generate first the nanopart, the inorganic rich phase within the lactide, and then polymerize the lactide. So again, the same slide, using hydrolytic or nano-hydrolytic, and we use a catalyst, which is used with this ratio to get for the non-hydrolytic route, the condensation and reaction of the chlorosilane with an ethoxysilane. In that case, we use the tetraethoxysilane, which is well known in solvent chemistry, with some chlorosilane. And the second step, as we have the mixture in which we perform this first step, we continue and then go to higher temperature, 180 again, and with the common ring opening polymerization of the lactide monomer, in which already exists now this silicon-rich phase. So you have example of the morphologies which could be created in. So PLA tails with some, so that's the hydrolytic way. That's a mistake here. That's a non-hydrolytic way, and you can see that the non-hydrolytic way we have a quite nice dispersion, even better than the PLA tails, because the phase separation occurred in a different way. That's things which need to be investigated more, but which can be probably explained. The problem is that the PLA molar mass is not so high in that case, but that could be an efficient way to generate morphologies. That's quite difficult chemistry, the non-hydrolytic, because you have a lot of species which are created in between the chlorosilane and the ethoxysilane. And that's quite complicated, but we were able, by NMR and by looking to what we call PhD students call visible silicon, which means the silicon which is in the extractable phase, in the soluble phase, to see what